recognition that people find. And as I said before, they use, I'll talk a little bit about this. This really, you notice that when you do this kind of spectroscopy, you need a tunable photon source, right? Because you have to, just like your UV absorption spectroscopy, you need to somehow tune your photon, tune your energy photon. So here the X-ray photon energy, you have to adjust, continuously tune in order to measure the intensity of that. And in the before 1980s, it's not so easy to do because there's no source. Because as you can see, X-ray fluorescence, which is how people generate the X-ray, right? Lamp, how you get X-ray lamp, is really by this process. I go back to here, right? By this process. How do you generate an X-ray anyway? So what you can do is that you can use some electron source to excite your material and let the material decay from the excited state to ground state. And you get X-ray light because you get these resonant emission from there, right? So in the old days, people have these lamp, X-ray lamp, but then now you are telling me that I have to continuously change my photon energy of my X-ray. That's not so easily done. I need some sort of facility that allow me to turn my knob so that it can continue study. Because you simply cannot afford to have so many lamps that match together to generate a photon energy spectrum like this. So in that time, high energy physics facility have this annoying radiation called Brunstrom radiation. This is due to deceleration. So what happened in high energy physics facility, like Triumph is a good example in Vancouver. They have a cyclotron. So the cyclotron started with, so how does the cyclotron work? You started with a linear accelerator ejection into a ring, cyclotron ring, and it just circle around like this. Okay, and you are circling the electron beam. It could be an electron beam, it could be a positron beam, anything with a light charged particle. And then in the case of cyclotron, Triumph case, they are interested in collision physics, so they use this beam to collide with some material and then look for particles that come out. So that's how particle physics work. And people discover every time they go through this little cyclotron, they lose this energy. And this energy is called Brunstrom radiation. Brunstrom radiation is a word for breaking. It means breaking energy. Because when you try to accelerate the electron and keep it in the orbit, remember you're trying to accelerate the electron close to the speed of light. So you get the electron up to 99% of the speed of light, right? So extremely fast electron. And they have this Brunstrom radiation, and this is a nuisance because this interferes with the experiment. But then some guy noticed, well, this nuisance radiation, maybe we can use it somehow because they are X-ray emitting. If we can capture and monochromatize, tune this X-ray, you could have a variable photon beam. Okay, and so that's at that time that people discover, well, maybe we can generate a variable photon beam. So they design instead of designing a cyclotron, they design something called a storage ring. So they inject this thing, and then they keep this electron beam in orbit. Okay, keep it in orbit. Now, this is not an easy task to keep the electron beam in orbit, especially when it's moving in speed of light, because one small move you can crash your beam. The beam path is very small, and the electron has to go around in a circle. And you remember I said that every time it goes through a circle, the electron try to get back to the lower orbit, okay? And it's losing energy all the time, because this is how you get radiation coming out from each of these points, right? Like this, radiation coming out. And so what you need to do is that every time it goes through, you have two stations in each end somewhere around here. You need to boost the energy, give a little bit of energy back to the electron, without killing the electron beam, right? Because you have to inject energy back into the electron so that the electron keep going in the storage ring. Otherwise, you have a very short lifetime experiment, because once you go to this, you lose the electron beam. There's no way you can work like that also. So this is called a storage ring. What they have is that two devices called Klystron, and this Klystron is some way to inject the energy back into your electron beam, go around the circle. Okay, so we will talk a little bit about that, and this whole system is called a synchrotron. Okay, so this whole idea with a linear accelerator, storage ring, and then a beam line coming out to capture the radiation is called a synchrotron. And Canada has one in Saskatchewan. We'll talk a little bit about that later on in this lecture. So what you got is that you have a storage ring. Yes?
A simple question related to the previous slide. How do we preferentially excite only the 1s electrons?
You don't have a choice, because if you're using, so the question is how do you preferentially excite the electron? You don't, if you're using a fixed photon beam, you don't have a choice. You would absorb the entire photon, and then the material will decay the way it decays. So you would decay both the s electron and all the high upper state. It will also decay, but they would decay with a different probability. So the peak height, this peak height will be different depending on the photon energy that you absorb, and of course the valence band, the upper energy state, will also depends on that photon energy. So you don't have a choice. The material will decide. If you're using same thing with the electron beam, because they would have it will have different kinetic energy of the electron beam, and they will give you different probability. So your cross section will look very different. So therefore, it's important to know what is the excitation photon, because that will give you how the intensity changes if you do it at a different energy. Okay, and it's well defined, because you will know what electron it is by looking at the so-called binding energy of that electron. So it is quite well defined, even though you cannot differentially absorb that photon. So we have a synchrotron. We can change the photon energy at will. Okay, we have beam line, and at the end stage, so this is a typical synchrotron beam line. So you have a big synchrotron is drawn up to scale. And this is correspond to Stanford synchrotron is called SPEAR, and it's a very large synchrotron, underground synchrotron in Palo Alto, California, and then you have different beam lines sticking out, and you got different mirror. Okay, these are metallic